Okay, so we continue to have our uh, PD reading seminar. We have Yang today from Johns Hopkins, and he's gonna talk about anist anisotropic Bernstein problem. Okay, please.
Yeah, thank you so much for the introduction and the invitation. Yeah, I will, as the Professor Chen introduced before, I will be joining UW Medicine in this fall. I'm very excited. Okay, so today I want to talk about the anisotropic Bernstein problem. And this is the problem of classifying the global solution to a class of equations which arise in geometry and surface equation. Okay, so to begin with, I want to first introduce the background. Uh, so around 1915, uh, Bernstein proved this following beautiful and surprising theorem, the Bernstein theorem, which says the following. So if we have a smooth function u defined all of R2 and solves this nonlinear elliptic equation, the minimal surface equation, written in the divergence form. So divergence of gradient u divided by square root of 1 plus gradient squared is equal to 0, then u has to be linear. So what this equation tells us is that the graph of u is the minimal surface in R3, and the sum of its principal curvatures is equal to 0 everywhere. And and also this theorem says something kind of surprising to me, in the sense that if you rewrite this equation over a tangent plane to the graph of u, and then at the contact point to the tangent point, this equation reduces to the Laplace equation. So it's kind of like a geometric version of the Laplace equation, but the invariant on the rotations. On the other hand, we know there are many, many nonlinear global solutions to the Laplace equation. For example, you can take the real part of any holomorphic functions, like e to the e to the e to the z, which has really fast growth. So I think this is the situation where the nonlinearity of this uh, minimal surface equation helps us get a rigidity result. And the so-called Bernstein problem asks if one can if we can replace this R2 by Rn. So if this Bernstein theorem holds not just in two dimensions but all dimensions, and or if it fails, then if one could construct some counterexamples. So now this problem is completely solved, but I'd just like to spend short time just discussing some of the key ideas of its resolution, because it's important for the rest of my talk and also beautiful in their own right. So so first is Bernstein's original proof. In 2D, the answer is yes. This proof is highly non-trivial. It involves two parts: a topological argument, which does not involve the minimal surface equation at all, and the special observation that the union normal to the graph of function u is actually a conformal map. And the reason is that if you differentiate this union normal, you get the second fundamental form. And in 3D, it's just two eigenvalues for the second fundamental form, and they are of equal size and different sign. So he used the conformality to show that the union normal is actually a constant everywhere. So it has to be a plane. Uh, so if one attempts to generalize this 2D topological argument to higher dimensions, one immediately runs into trouble. So in order to generalize this Bernstein theorem to higher dimensions, some new ideas were needed. It was until 1962, Fleming came up with a new idea which really had hope of generalizing to higher dimensions. And his idea is based on something completely different, which is the observation that if you have a minimal surface in any dimension or any codimension, then either at a very large or very small scales, it has a cone structure. So it's the content I think is called the monotonistic formula. And then by using this monotonistic formula, it showed that if you have a nonlinear global solution to the minimal surface equation, then you keep zooming out, zoom out, zoom out. Then some subsequence of the zoom outs converge to a non-flat area minimizing hypercones. So he reduced the problem to deciding whether or not there exist such non-flat area minimizing hypercone. So for example, by using Fleming's idea, one can quickly recover Bernstein's original proof. So if you have a nonlinear global stage solution in R3, then you have a non-flat area minimizing cone, right? But intuitively, it is not possible because in R3, there are just two curvatures you are dealing with, and one of them is automatically zero by the cone structure. So the other one has to be zero because the mean curvature, the sum of the principal curvatures is zero. So the cone has to be flat. So yeah, after Fleming's proof, people really jump onto this problem, and in a matter of say, looks like 7 years to completely resolve this problem. So in 1965, George made a small improvement of Fleming's result. He showed that the area minimizing cone has a very special structure, which is a slitting Jerkow structure. So each horizontal slice of the area minimizing cone in R4 is a copy of area minimizing cone in one lower dimension. So he gained one dimension compared to what Fleming could do. And for dimension 4 and then until dimension 7, Umgren and Simons showed that so for all such cones in low dimension, they have to be flat. So in fact, they didn't use the whole information that the cones are area minimizing. So all they need is that the cone is minimizing on the tiny perturbation. So small perturbations increase the area. So for all such cones, they should be flat in low dimensions. So this uses I think the stability inequality. And finally, in a remarkable paper of Bambier, George, and Giusti from 1969, they showed that the Simon's result is sharp. So by constructing a nonlinear global solution to the minimal surface equation in R8, which has cubic growth. And I will discuss a little bit more about this example later. Okay. So yeah, so now there exists nonlinear global solution to the minimal surface equation. So at this point, it's natural to ask if one can add some additional conditions so that Bernstein theorem still holds. And indeed, there's some natural candidate one could impose. For example, if one can put some Bruce conditions. So first, if you assume that if the gradient for U is globally bounded, then U has to be linear. So this is because if the gradient of U is globally bounded, then the equation becomes uniform elliptic in this case. So the Harnack inequality of DeGeorge and Nash can be applied. And if you assume we can kind of relax this condition a little bit. We can integrate, for example, integrate this inequality. We assume that U just has linear growth, then U has to be linear. This is because if linear growth implies the gradient is globally bounded. This is by the interior gradient estimate of due to Bambier, George, and Miranda from 1969, which is extremely important advance in its own right, and is in fact used in many contexts, also by Bambier, George, and Giusti to construct a Conte example. Okay, so the best result I know to date is that if you assume that the gradient of U grows slightly slower than linearly, then U has to be linear. So this is the result of Aken-Huskin from 1990. So this result is basically sharp in the sense that if you look at the analogous of Bambier, George, and Giusti's example in high dimensions, then nonlinear global solution grows like a big O of x to the power 1 plus 1 over dimension. So when the dimension becomes higher by higher, this estimate gets better and better. So there's no much hope that one can improve this result very much. Okay, so at this point, I basically finished discussing the Bernstein problem for minimal surface equation, and I want to move slightly a different direction. And the direction is motivated by the question that if the minimal surface equation may be just part of more general part of a family of more general elliptic equations, so that Bernstein theorem holds. And the answer to this question is yes. And this comes from studying the so-called parametric elliptic functionals. And the object of interest right now is still hypersurface in Rn plus one. But instead of asking the minimized area functional, asking something a little bit different. So it's sort of like a weighted area functional. So it's the integral of the area function of the area element, but weighted by a function depends only on the unit normal of the surface. So we can think that if we have a minimizer of a functional like this, then rotation will not keep the problem invariant. So we lose rotation invariance for this kind of problem, unlike the minimal surface. And what we assume about this weight or this integrand phi is that it's one homogeneous on Rn plus one, and it's a norm, so it's a positive and smooth from the sphere, and it's convex. So it's a level set of its function phi are nice, uniform convex sets. So this is what we mean when we say this elliptic functional. And the reason is regarded as uniform ellipticity. I think that it's easy to see when you look at an equation that the critical point of this function satisfies. So if you take the first variation of this functional, you look at this Euler-Lagrange equation, which will be the second derivative of phi. You take the trace with the second fundamental form of the surface, and this is 0. And basically, this equation says that the principal curvatures are balanced. The sum of the weighted principal curvatures equal to 0. So if phi was the area case, then phi of x is equal to mod x. Then this the Hessian of phi becomes the identity matrix. So the sum of the principal curvature is equal to 0. Mean curvature is 0. For the general phi, we assume that the eigenvalues of this Hessian of phi is between two positive constants. So sort of like a geometric version of the uniform ellipticity. And what we the so-called anisotropic Bernstein problem asks exactly the same thing as before. So if we have a minimizer of a functional like this, which can be written as a graph over all of Rn, and it is necessarily a hyperpoint. Okay, so now I want to first connect this geometric version of the equation to a PDE I'm gonna work with. So, so the way I like to view this sigma, the hypersurface sigma, can be written as a graph of U. And this the nu is just the unit normal of this sigma. Then this geometric version of the equation can be written as this quasi-linear elliptic equation. And this the per psi ij of grad u times uij is equal to 0, where this function per psi is just function phi restrict the hyperplane tangent to the sphere at the North Pole. So so because we assume this phi is one homogeneous, so we do this restriction, this per psi is just asymptotically one homogeneous. So so this quasi-linear elliptic equation degenerates as this gradient u gets very large. And it degenerates in the same way, in the same fashion as it does for the minimal surface equation. So to see this equivalence of these two equations, I think it's easiest to see when you rewrite everything in terms of function u. So if you rewrite this to the unit normal in terms of function u, and also the area element in terms of u, then by the one homogeneity of this function phi, you get this last functional. So this quasi-linear elliptic equation is just the Euler-Lagrange equation associated to this last functional. Okay, so yeah, and then the anisotropic Bernstein problems recently completely solved, but I just like to spend a short time to discuss the history. So in dimension 2, the answer is yes. So for all global solution to any type of anisotropic area functional, they have to be flat. And this this due to Jenkins in 1961. So again, he used the complex analysis, but instead of being conformal map, and now it's a quasi-conformal map. And again, a lot of times when I see a theorem is true in 2 dimensions, I don't necessarily have a lot of hope that it can be generalized to higher dimensions. In particular, if the proof is based on some special 2D topological argument or some special energy estimate. But surprisingly, Leon Simon managed to extend the theorem to 3 dimensions. And the reason is that surprisingly is that if you remember, the key factor we need to extend the Bernstein theorem to higher dimensions for the minimal surface case is the monotonicity formula. And this is something we lose it for the anisotropic case. But anyhow, Leon Simon still managed to extend the theorem to 3 dimensions. And unsurprisingly, the proof is quite sophisticated. And Leon Simon did prove relies on some very deep regularity theorem due to Armagund Simon around the same time for parametric problem. And so after Simon's proof, it really made us think that maybe for the anisotropic area functional, the magic number 7 will still appear like the area case. So up dimension 7, we can find nonlinear global solution. Below dimension 7, they are all flat. So maybe for the anisotropic case, it's still the same thing. Or the isotropy is really the key that when we relax the isotropic to the anisotropic case, then one can expect to build some counterexample in lower dimensions. So in 2019, so Mooney gave the answer to this question. So indeed, when we relax to the anisotropic case, one can construct some counterexample in lower dimensions. So he constructs some nonlinear global solution to a class of anisotropic area functional in 6 dimensions. And just 2 years later ago, we construct a counterexample in 4D. So this problem is completely solved. So for the rest of the talk, I will focus on these 2 examples. So before I jump onto the explanation for these 2 examples, I want to first talk a little bit about Bambier, George, and Justice example, as I promised before. So because our approach for constructing the 4D counterexample is motivated by the approach. So this is the area case, the area the minimal surface case. So the phi of x is equal to mod x. And the counterexample is built on R8, which will be split into 2 pieces, R4 cross R4. And the starting point for this, look for non-flat area minimizing combs. So one of these has to exist in order to exist nonlinear global solution. And I think the most natural candidate for this is the so-called Simon's comb, which is mod x equal to mod y. So I think it would be easier to just look at this picture to explain what they did. So it's R4, so it's R8, so R4 cross R4. And this is Simon's comb mod x equal to mod y. So in these 2D pictures, it just looks like the 2 diagonals. So it's a good candidate because this is symmetric. So it looks the same from both sides. So it has mean curvature 0. And so it's a critical point of the area functional. And the starting point for that is to show that this Simon's comb is not only a critical point of the function of the area function, but also a minimizer of the functional. So they did this by showing that there exists a smooth perturbation of this Simon's comb, which I call sigma here, which is the minimal hypersurface and is asymptotic to this comb at infinity. And this hypersurface lies on one side of this Simon's comb, which is very important. So this relies on some very deep, very careful ODE analysis. So this sigma has the same symmetry as the Simon's comb. It's a rotation invariant of the x and y. This is why it can be reduced to an ODE problem. But the point is that all the dilations of this hypersurface then foliate on one side of this Simon's comb. So there's a general principle says that if you have a foliation of some space by critical points of the functional, then each of the leaves of the foliation is the minimizer of the functional. So this is the so-called, I think, calibration argument. So, so then they show that in fact, the Simon's cone is area minimizing. And then there's something quantitative what I want to point out is that there's a very specific approach rate of this hypersurface to this Simon's cone. And the way I like to view this is that if you go distance out from the origin, then the distance between Simon's cone and the hypersurface roughly r to the -2. And this exponent of -2 comes from studying the geometry of the Simon's cone, the Jacobi operator of Simon's cone. But the point is that in order to construct a nonlinear global solution to the minimal surface equation, the idea roughly is that the level sets of the global solution are supposed to look like the leaves of the foliation. So you can think that if the global solution takes 0 on this sinus cone, takes value 0 on the sinus cone, and then 1 on this hypersurface sigma, then it goes from 0 to 1 over distance r to the -2. So which means that the gradient of the global solution should grow something quadratically, and so the global solution itself should grow something cubically. So then notice that the global solution, the one level set of the global solution resemble this cubic homogeneous function, r cubic times cosine 2 theta, where this r is just the x squared plus y squared, and the theta is just like polar coordinates, mod x more equal to mod y. And they know, and after some short computation, they can show that this cubic homogeneous function is in fact a subsolution where it's positive and super solution where it's negative. And this part is easy, and the hardest part in their paper is to show that there exists a perturbation of this cubic homogeneous function, which still has the same cubic growth, but it becomes a super solution where it's positive and sub solution where it's negative. So switch the sign on the same region. So if you look at the paper, this part is really like for me it's like magic. They just build up this super solution and then show that yeah, I think this part is really magic. I don't know what the motivation behind this construction. But the point is that once you equip it with these super and sub solutions, you can just solve the differential problem in the larger and larger balls, and then you take the limit. So the solution to get the solution. The solution should be trapped in between these two super and sub solutions, and it should have the same cubic growth rates. So this is their approach. Okay, then I'd like to start to talk about the 60 example. So in 2019, we showed that exists a quadratic polynomial on R6, and whose graph minimizes some anisotropic area function. So there's some remarks I want to bring up is that first, this answers the question whether or not there exists a nonlinear polynomial solution to equations of minimal surface type. That is kind of interesting. And the second remark I want to say is that this integrand phi should be far from the area case, which is one. Sorry, I say this. Far from the area case, which is just the one level set of the area functional is just it's just a circle. So actually, the one level set of this function phi he constructed is of box shaped. So it's far from the circle. And this is necessary because Leon Simon showed that if phi is close to the area in C2 topology, then all the global solutions, they have to be flat in low dimensions. Up to dimension 7, they have to be flat. So it's necessary that phi should be far from the area case. Okay, so I want to spend short time discuss the resolution. So Mooney's approach is completely different with the Bombier-Georgian and Giusti's approach. So the reason is that when we with this anisotropic area functional, we have the freedom to choose the integrand. So the approach for Mooney is to first fix the option of the solution u, and then go backwards to solve for function phi. So So he's just choose this simplest possible example, x squared minus y squared. The reason he chose this as a candidate solution is that anytime you look for a solution to a certain equation of minimal surface type, it should be of a saddle shaped, and this guy is of saddle shaped. and uh, and the trick is that he used the Lorentz transform to transfer this nonlinear quasi-linear elliptic equation to a linear one. If you're not familiar with the Lorentz transform, it's fine. It's just a transformation on the gradient space of U. And so he can transfer this nonlinear equation to a linear one. And so the Hessian of U just becomes the inverse Hessian of the Lorentz transform of U. So at this point, he just solved the Cauchy problem to this the linear hyperbolic equation. The reason it's hyperbolic is because this guy's of saddle shape. So the eigenvalue, so this how can I say that? So the Hessian of this Lorentz transform has positive signature, so it becomes a hyperbolic problem. So that at this point, the trick is to solve this linear hyperbolic equation, and then the way I like to view this, you can try to solve this this equation so that can I say this? You can solve every possible phi so that the crystal surface, I mean the graph of U can minimize this function, minimize the functional. But the point is that you can. But the point is, the hardest part in his papers to show that this phi satisfies the desired convexity condition. Uh, this is the hardest part. Uh, so in 60, fortunately, so he can show that there indeed exists some phi which solves this equation, also satisfy this desired convexity condition. And then one could ask if one can use the same strategy to prove the 4D case. The answer is no, because if you choose this quadratic polynomial, then in 4D, no matter what phi you choose, it will not satisfy the desired convex condition. So in order to construct some counterexample for 4D case, we need to go back to the Bombier-Georgian juice approach to build up super and sub solutions. Okay, so there's one thing I want to point out is the level set of function phi is of box shaped. So it's just one level set. It goes slowly along this sinus cone direction, than the axis direction, which is kind of makes sense because if you look at the graph of this function U, then overwhelmingly the unit normal view points to the sinus cone's direction. So it's reasonable that we expect the integrand should go slower along this sinus cone direction other than this axis direction. Yeah, so from the variation point of view, it's kind of natural. Okay, and then I want to talk about the 4D case. So we showed that there exists a smooth linear function from R4 to R, and whose graph is a minimizer for an anisotropic area functional on R5. And something I want to bring up is that first, this example has a variety of growth rates. So the global solution we build up, they have many growth rates. This just not has one growth rate. So actually has the growth rate r to the 1 plus mu for any mu in between 0 and 1/2 in 4D. And also, bring up is that our methods can be easily generalized to higher dimensions. Also, it can recover the example by Bombier-Georgian juice. Okay, so starting point, I want to first explain some notations. So CKL represents the cones in R K plus L plus 2, and mod X is equal to mod Y. So our starting point is as the Bambio-Giorgi to build up the foliation on both sides of this cone C11. In R4, it's just the cone is called C11. Yeah, what we showed that is that for any mu in between 0 and 1/2, we can prove the exist elliptic integrand per sidebar such that on each side of the cone C11, uh, we can build up a sub 5 bar minimizing hypersurfaces. And also these hypersurfaces resemble the level sets of this 1 plus mu homogeneous function. I think it's easier to just look at this picture. So it's in R4, so we split into R2 cross R2. And this is our cone C11. And yes, the Bambio-Giorgi we find a smooth perturbation of this cone C11, which is sigma, and is the A sub 5 bar area minimizing. And it has the approach rate to the minus mu as this hypersurface goes to the sinus cone. And it can be also written as a graph over X. Okay. Yeah, the condition that sigma as a critical point is equivalent to solve this ODE. So this we prove that this hypersurface lies on one side of this cone C11. This relies on analyzing this ODE, which is to get this ODE, we just plug everything to the if you remember, to the quasi-linear elliptic equation in terms of this sigma and in terms of this function phi. And then at this step, we fix our choice of nu and per sidebar. Okay, so we are good. We have the foliation of both sides of the cone C11, and then we try to build up the global solution. So the first step is to linearize the previous nonlinear ODE. We need linearize the ODE, and we perturb the foliation, the leaves of the foliation, so that it has strictly positive and negative anisotropic mean curvature. So which I call sigma subbar and sigma superbar here. So they will have anisotropic mean curvature pointing towards or away from the C11 cone. This I think it will be intuitive to look at this picture. We perturb this foliation, and then so that it has positive and negative and anisotropic mean curvature, and it keeps the same approach rate at infinity, still r to the minus mu. This is important. Okay, so we just build on this. We build on the super subsolution based on these leaves of this foliation. We just define the function w superbar and w subbar, which are 1 plus mu homogeneous, with level sets as this Simon's cone, which takes 0 on the Simon's cone and takes value 1 on this sigma subbar. And for w superbar, it takes value 1 on this sigma superbar. And then plug this after some shortcut, because they are homogeneous functions, so we can easily show that they becomes a super solution with positive and sub solution with negative. And but the issue is that this is not the equation we want to solve. If you remember the quasi-linear elliptic equation we want to solve, this guy should be asymptotically one homogeneous, because this guy is just a restriction of the one homogeneous function. But here, this per sidebar is one homogeneous. So this is the problem. This is not the equation we want to solve. So to fix this, we have to modify our function per sidebar a little bit. We want to make this to be a smooth function and an asymptotic one homogeneous. So to rebuild this function per side, what we do is that we make this function per side to be one square root of 1 plus per sidebar square, and this motivation comes from the area functional. yeah, the average function is just 1 plus a square root of 1 plus gradient square. Uh, so this guy now, psi, is now becomes asymptotic one homogeneous. And it turns out that we only need to do this modification, this modification outside of B1. So we don't care about how we extend this function inside B1 in test. It turns out it doesn't matter how we extend it. We can just choose any arbitrary extension inside of B1. I will get to this point later, why we don't care. Okay, so now we are good. We changed this function per sidebar to a asymptotic one homogeneous function, and it's smooth. But point is that we mess up this equation a little bit because we changed this guy, so we don't have the superand solution, a superand subsolution on the whole region anymore. So we mess up this equation. So in order to fix this issue, so far we just take advantage of the curvature along the how can I say that, on the level sets. So we still have one remaining vertical curvature we didn't take advantage of. So the way we do this is we stack the level sets of W subbar and W superbar. We compose this W subbar and W superbar with the functions H superbar and H subbar, so that we can take advantage of the remaining vertical curvature. So far, we just use the curvature of the level sets. So for example, to construct a super solution, we just make this U superbar to be the previous H superbar composed with this W superbar. So it looks technical, but the point is that we don't have the super solution on the whole region anymore. So in order to make the equation more negative, we just make this H superbar to be a concave function. So if you look at the second derivative of this function, it is negative. So it's concave. So when we differentiate, we get something negative. So this is what we want to do when we want to make this to be a super solution. And also, we want this to be extremely concave because, okay, let's say this. Right. The point we add on this turns that we want to make this solution to be extremely concave near the Simon's cone. And so that's why we make up this term here. And also you can see that this H has linear growth at infinity. So as S goes to infinity, this just goes to 0. So it has it goes to 1. So it has linear growth rate. So it would not change the growth rate of function per sidebar, W superbar. It remains the same 1 plus mu growth rates at infinity. And it turns out, it turns out when we choose this B and A carefully, we can make this U superbar to be a super solution on the whole region with positive and sub-solution with negative. And for the sub solution, it becomes easier. So we still do the same thing. We compose this W subbar by a function appropriate function H subbar, which you can see that this is convex function. So because when you take the derivative, we want to make this equation to have more positive terms. And then we don't necessarily need to extend this not to be a sub-solution for the whole region. What we did is that we make, let's look at the picture. We just make this U naught to be a sub-solution on this red region when the U naught becomes very large. And then we can just truncate this function with the height and take the maximum between the function and 0. So this guy still will be a sub-solution. We just truncate U naught with the height and then take the maximum with 0. So this guy will still be a sub-solution. And then we can just use the odd reflection to get the other to get the opposite sign on the the other region. So yeah, so now we have these super and sub solutions, and then we can just proceed as Bambia-Giusti, solve the dirichlet problem in the larger and larger balls, and then take a limit so that the to get the equation, so that the equation will have the same growth rate as the super and sub solutions. So this is our approach. And then again, yeah, our approach is kind of a systematic than the Bambia-Giusti approach. Our way to build up the foliations and then to perturb the foliation and then cook up uh, the super and sub solutions kind of a systematic. So it can be generalized to higher dimensions, also cover Bambia-Giusti example. But another remark is that our approach does not work for the case when case not equal to L. Because if you remember, to build up our sub-solution, we need to use the odd reflection. But if a case not equal to L, we cannot do this any longer. So yeah, so it would be interesting to find a global solution. I mean to this yeah, to find a, can I say that, to construct the same global solution to which has the asymptotic goes to this CKL cross R. Okay, so this is all we have to talk about today. We could leave you guys to ask questions.
Thank you, Yang, for the great talk. Yeah, we have time for questions. Please unmute yourself. So while we are waiting, let me ask, so I mean, as you mentioned, it's for even dimensions. What happened with five?
I'm sorry.
I mean, like,
Sure. It's
yeah.
it's a good question. Let's go back here. Yeah, so yeah, once we can build up some equation in dimension 4,
Mhm.
the kind of example in dimension higher is automatic. We can just make it constant in the
Right.
remainder directions.
What I mean is that, is there any kind of like, of course, you can make it constant, but what I mean is that is there, any hope to construct anything different in dimension five?
I see. So yeah, as I mentioned before, for dimension 5 is odd. It's odd dimension. We cannot split into a two equal. Yeah, cannot. For example, for the 4D case, we can split in R2 cross R2, but R5, yeah, our approach does not work for R5. We can just do this trivial construction. Yeah, some non-trivial construction still remains open, I think.
Yeah, please ask questions before we start our informal discussions.
So can I ask one?
Yes.
Go ahead, please.
So does it make sense to consider the anisotropic problem for the shrinkers instead of minimal surfaces?
Yeah, so sorry, I'm a more PDE person. Sorry, even though it is a geometric problem, but I don't quite understand shrinkers. Sorry about that.
Oh, okay. So then what about like in high codimension? So we consider
Uh,
a vector value graph, say on R2 in Rn. Is that any results?
yes, I think there's some. I'm not 100% sure, but I think there's some result for high codimension anisotropic minimal surfaces due to Antonio de Rosa and Guido de Phillips. I think they have some result there. But yeah,
Uh-huh.
this is all I know.
So what about for like regular minimal
Regular,
surface?
I see.
I mean without any stropic, just like the regular minimal surfaces. I mean the minimizer of the area. So in high dimension, is that like well understood?
I'm sorry. Oh, you mean for minimal surface in high
Right,
dimension?
right, right.
Yeah, for minimal surface in high dimension is another topic. I think it's called minimal surface system theory, and the theory there is quite wild. So I think, yeah, Yeah, I think let's see. The monotone is let's see. There's some very wild counterexample on this minimal surface system, even in lower dimension. So I think this counterexample constructed by Lawson and Osserman. They constructed nowhere C1 solution to the minimal surface system in I forgot in 3D or higher, I forgot. Yeah. So the case in the minimal surface system is quite wild. A lot of the properties works for the minimal surface case failed there. So yeah, there just has very few known result for that direction. But I remember
Okay.
my advisor Connor Mooney, they just solved. I think he solved the Lawson-Osman conjecture in 2D for arbitrary codimension, which says that
Oh,
if you have a yeah, so the if you have a minimal map from R2 from B1 is lies in R2 to any
mhm,
codimensions,
mhm.
then it solves the graph solves the minimal surface system equation, then
Mhm.
it has to be yeah. What we assume that is the U is Lipschitz, and then it has to be smooth since the is what Mooney showed, but it's just two dimensions. So in high
Okay.
dimensions, there's a lot of counterexamples.
Right. There's a recent paper by Connor Mooney and Ovidiu Savin. You can have a look. Check. I
Yeah,
mean,
Okay, thanks.
are there other questions for yeah? Okay, so if not, then let's thank Yang again for a great talk, and then let me stop recording.